one? Yeah, you are for real. Okay. Anyway, I actually, it's funny, I went for a really big run on Monday. I walked out the door, so I just have to share this with you. So, you know, I get an MRI every 4 months now, and before my MRI, but between my MRIs, I swear I have to do a 20-mile run. That's just a given, I have to do a 20-mile run. So on Monday, I was gonna go for my 20-mile run, so I go outside the front door and immediately trip and fall, and like my knees are just blood patches. This arm is like good and bruised, you see that, and then anyway, and then this shoulder hit and hurt. And I totally forgot why I was telling you. Oh, no, it's because but I did get up after that and do a 20-mile run. But anyway, my arm might hurt, so I might whine a little bit, but I actually landed on my hand and it's bugged my shoulder pretty bad. So I might have to have one of you come up here and write on the board. Okay? It's gonna be the top card. Anyway, so, yeah, so our issue was that we were trying to do this counting, and I said if we take from rest, and this is deep in the discussion, so if you don't recall this, that's fine, don't worry about it, but I said if you take, in the rest frame, energy minus MC 0, 0, 0, then the Dirac equation becomes I gamma naught MC psi plus MC psi equals 0. And then you can actually write down what I gamma naught plus 1 is. It takes a very simple form, and then we found that for the parts of the 4-component solution of this, these are psi's, not 4's, that this equation imposed this condition, psi 1 equals minus psi 3, and psi 2 equals minus psi 4. Okay? But then later on, I showed you the proper at-rest solutions to the Dirac equation, and it turns out that in addition to these, and these basically take the form 1 minus 1, 0, 0, etc., okay? We also had solutions of this form, okay? So we seem to be getting an inappropriate number of solutions. We have the solutions to this, which there were only 2, and then we had the solutions to the Dirac equation, of which there was 4. However, what we interpreted from our set of 4 solutions to the Dirac equation was that 2 of them actually constitute antiparticles, not particles. And also there was the energy part of that story. And in one case there's a plus here, and in one case there's a minus there. So one way to interpret antiparticles is that they're negative energy states. Okay, or you can talk about them going backwards in time. We prefer for them to go forwards in time, so they're negative energy states, but that means that the sign of this would change. So in actuality, this is only half the set, the other half of the set would satisfy this. Because remember, in the 4 momentum, the first component is E over C, and then when you dualize it, you get a minus sign. But if this energy is negative and you dualize it, you get plus. So this is the missing second set of solutions that we found to the actual Dirac equation. It's because we went into this analysis doing this little counting trick without realizing that we were going to have negative energy solutions. Okay? So that was the resolution to that little puzzle. Now, today is going to be a shit show. Today we're going to just dig so deep into Spinors that you're going to leave feeling spinorially drunk. First of all, I promise next Tuesday's lecture will wow your pants off. It'll be amazing. It's one of my favorite topics for the entire semester, so just suffer through this and then get to Tuesday. What we're going to talk about today, we will not employ for quite some time. It is just a really, really crispy aspect of Spinors, which is just going to seem really sort of frivolous, but it is actually, what we're going to talk about today is actually going to play an incredibly critical role, not just in the weak interactions, but in the Higgs mechanism as well. So this is just a detail which we have to go through, and unfortunately it's kind of ugly, so just bear with me. So I finished last time, let's see, yeah. I finished last time by just giving you stationary solutions to the Dirac equation. These are all getting out of order. reminder of what those look like, we had psi1 rest, and I'll just write one of them up here. It's e to the minus I mc squared over h bar times t, 1 over root 2, 1, 0, 1, 0. And then basically we get two other, well, I'll just write them up here. I'll write these up here. So this is solutions 1 and 2. And solution 2 goes like 0, 1, 0, 1. So it's the same coefficient, it's just got 0, 1, 0, 1. And then for psi 3 and 4, we have e to the I mc squared over h bar t, 1 over root 2, 0, 1, 0, minus 1, and minus 1, 0, 1, 0. Okay? So again, those are at-rest solutions, so these are obviously massive particles, at-rest solutions to the Dirac equation. And one of the things that I want to point out to you is that if we apply Sz, which is the z component of spin, so you might or might not recall, but for spinors, the z component of spin simply ends up being h bar over 2 times sigma z, 0, 0, sigma z, okay, where the sigma z's are just the Pauli matrices. Okay, and I gave those to you some number of lectures ago, but these are the 2x2 complex matrices. So this is a 4x4 matrix. Everything is written in terms of smaller 2x2 matrices. The sigma z is the z component of the Pauli matrices, the Pauli matrices. And then these zeros are 2x2 zeros. And in fact, if I actually write down what this matrix is explicitly, it's 1, minus 1, 1, minus 1. Okay, so it's not quite the identity, but it does just have ones down the diagonal with a few special minuses. Now, what we discover is that if we apply this to the solution, say 1, okay, what do I get, Sean? If I apply this matrix to this spinor right here, this one right here, what do I get?
You get the same spinor out?
Yeah, I get the same spinor out with a factor of h bar over 2. Okay? Oh man, we're going through a lot of them today. Sergio, you here? Sergio is not here. He's probably going to show up late. Shaylee. Let's see on psi 2, that's this guy.
Psi 2 with a factor of h bar over 2?
Psi 2 with a factor of h bar over 2?
Yeah.
Well, look at where the non-zero terms are.
Oh, so negative?
Yeah, you'll be picking up these negatives. So negative h bar over 2 psi 2. And then, oh boy, it's going to be so much fun. Jared. It's not here. PJ. PJ, what are you going to get when you apply it to psi 3?
After h bar over 2, but then the negative h bar over 2.
Yeah, don't worry about that negative. What's important is that this is the second and fourth term, which is negatives here. Okay? So it's minus h bar over 2 psi 3. And then I'll just do the last one. Sz acting on psi 4 is h bar over 2 psi 4. Okay? Now, an important observation, which is going to play an important role later on, is that these 4-component spinors are all eigenspinors of the z component of spin. Does everybody see this? All right. This is not going to be the story in a few minutes. And in fact, it's going to open the floodgates for the crap we're going to talk about. So I just want you to cherish this simple idea because it's going to get upset. Okay? So once again, if you're in a rest frame of a spinor, solution to the Dirac equation, and you measure the z component of spin, these solutions are eigenspinors. You get the same spinor back with a coefficient, an eigenvalue, okay? All right. So, what we need to do now is get away from spinors at rest. Because after all, in the calculations relevant for experiments, we're usually shooting things into other things and then things are flying out. So really we need to describe these things in motion, okay? Now, if you want to describe something which is in motion, you obviously can't pick that really super simple four momentum like you can for the rest frame, which has just got that 0th term being not 0 and everything else being 0. But you can assume a relatively simple form, and that's a plane wave solution, okay? So what we're going to do now is we're going to write down, we're not going to solve, but we're going to write down the solution to the Dirac equation, assuming a plane wave form. The derivation of this solution I will include in my notes. I'm just not going to go through it in class because we don't have the time. It's one page, but it's a lot of detail. But if you want to see it, it will be included in my notes for today, okay? So here we go. I'm going to try and maintain this and just go over what we're talking about. So this is the at-rest story. And now let's go in motion. So in motion, we want to assume that the spinor takes the form of a plane wave. So we're going to assume some amplitude times e to the minus I k mu x mu times some spinor, which might depend on the momentum, or this 4-vector k mu. We'll talk about what that is in just a moment. Okay? So this is the usual exponential factor for plane wave. So this is a scalar quantity. This is a scalar. This embodies the fact that this is a spinor. So this is going to be a 4-component object. It's just like these. You get these coefficients times this spinor. This guy is going to be 4-component, and that's going to capture the fact that what we're solving for is a spinor. Okay? We're solving the Dirac equation. The solution is a spinor. All right? Now, in order to do this, what we can, of course, say is that for this to be a plane wave solution, we want d mu psi, or this is just true, d mu psi is minus a k mu of psi. And then the Dirac equation becomes I h bar gamma mu k mu minus mc psi equals 0, which is, of course, an algebraic equation. Okay, we don't have a derivative in here anymore. All right? Okay, so after some work, we can show that k mu is equivalent to plus or minus 1 over h bar p mu, where p mu is the 4 momentum. Okay, so that factor of k mu is just the 4 momentum divided by h bar. Okay, and now I'm going to write down the 4 solutions which correspond to particles which are in motion, starting with psi 1. Now, I have a question. In the at-rest case, we found the time dependence here times whatever we do times what's basically a constant spinor. And we found that for all 4 solutions. The time dependence was basically in the coefficient. When you've done spinors, how many of you have done spinors in non-relativistic quantum mechanics? Nobody's done a spinor in non-relativistic quantum mechanics. How many of you took non-relativistic quantum mechanics? And you did not see spinors at all?
They probably just went.
So, oh boy. So, in non-relativistic quantum mechanics, I'll just write this over here. In non-relativistic quantum mechanics, spinors almost always played the following role. You had a wave function describing the position dependence times a spinor, where the spinors were basically alpha 0, 1 plus beta 0, 2, or sorry, plus beta 1, 0. anyway, it's fine. Or alpha and beta are just coefficients, okay, telling you what kind of superposition of these constant spinors you're using. So basically there's this separation between the position dependence of things and the spinorial nature of things. The spinors are just constant. They don't care where you're doing and where you are or what you're doing. They're just these fixed things. And then the position dependence, and this also involves the momentum because the momentum is controlled by this factor. The momentum is all in this scalar prefactor. It's not a part of the spinors. That's also what we found here. The behavior, the time evolution, is contained in these cofactors. They're not contained in the spinors. So it's true at rest, and it's true in non-relativistic quantum mechanics. It ain't gonna be true no more. Okay? And that's the headache that we're going to encounter, or part of the headache. Okay? So let me just write down one of these solutions, and then you'll hopefully just immediately go, oh, I see, that's a pain. So we've got A, e to the I, p mu, x mu, over h bar. That's just a generalization of this. Okay? This factor mc squared is basically p mu x mu if you're in the rest frame. So this is really kind of the same set of coefficients as in this at-rest story. All right? Of course, this is p mu, and if you're not at rest, p mu has more terms in it because it's got that spatial momentum. Okay? So remember here, p mu, p lower mu, is minus e over c 0 vector. Here, p mu is minus e over c spatial momentum. Okay? And also, E is mc squared, so this is, of course, minus mc 0 vector. Here you can't say that because at rest, or if you're moving, your energy is more than mc squared. Okay? So this is the coefficient, and now we're actually going to look at the spinor. The spinor turns out to be E over mc squared minus the z component of momentum over mc minus the x component of momentum over mc minus I times py, the y component of momentum over mc, 1, 0. Okay? And now I'm just going to scribble up the others. Side 2. And yeah, I'm going to write it down. I can't shorthand it. And then the side 3. Where you immediately notice the negative and the exponent, indicating that these are antiparticle solutions. And last but not least, side 4. Minus px over mc minus I y over mc. Okay? Now, I want you to go ahead and absorb this very interesting fact. There is no way that you can just pull out this energy and momentum dependence into a coefficient. Because, right, if I have a coefficient like these, they multiply every non-zero component of the spinor in the same way. Obviously, all of these factors are playing different roles in the spinor. Okay? So, there is another bit of notation, this is going to be a notation-heavy lecture. Another way to write these is that this is a e to the I p mu x mu over h bar times u1, a e to the I p mu x mu over h bar u2, a e to the minus I p mu x mu over h bar v1, and a e to the minus I p mu x mu over h bar v2. Okay? Where obviously the u's are spinors describing particles, and the v's are spinors describing their antiparticles. Okay? Now, it might not be obvious, but if you take these general solutions, well, these plane wave solutions, sorry, they're not general, but these plane wave solutions, and you simply say, well, I want this thing to be at rest, which you can always take the general solution and put it at rest, then these will exactly reduce to these. Okay? Simple exercise, you'll do it in your homework. There's nothing hard about it. Okay? But you'll see these contain the same information here, but these obviously contain a lot more because they include non-zero momentum descriptions. Now, okay, so one of the interesting observations, which I suggested to you is going to play a very important role in this story today, is that for the spinors at rest, as well as non-relativistic spinors, we have eigenstates of SZ. We can ask, are these eigenstates of SZ? Okay? So let's just have a look. If I do SZ of psi 1, then again, this is h bar over 2 times 1, or times 1 minus 1, 1 minus 1. That's the SZ operator. And then it is, of course, acting on psi 1. Oh boy, I think I already see the problem. Does anybody see the problem? Is this in any way, shape, or form proportional to the thing we started with? Nope. Does everybody follow that? Yeah, I mean, you know what's magical here is I have 2 non-zeros and 2 zeros. 2 non-zeros, 2 zeros, 2 non-zeros. That's where it works. Here, I've got 3 non-zeros. Okay? So I am not going to just pick up 1s or minus 1s. I'm going to pick up 1, minus 1, 1. And that's going to screw up my story. Okay? So it turns out that psi 1 is not an eigenstate of the z component of spin, and neither is psi 2, psi 3, or psi 4. Okay? So, you know, perhaps you do, perhaps you don't remember, utilizing eigenstates to like specify the physical state of your theory, that's an important thing, okay? We want to use eigenstates. And for these 4-dimensional relativistic spinors in motion, talking about the z component of spin is just not a good way to go. Yes?
Is that alpha psi 1? Was that proportional to psi 1?
Sorry, it's not proportional to psi 1. I drew the alpha and then I planned on putting the stroke through it. I forgot, but thank you. Yeah, it's not proportional to psi 1. Okay, so this makes you wonder, can you do anything with spin? Because it turns out that most of the spin matrices, I mean, you know, you'd have to go back and look at the structure of these spin matrices, but most of them have like, you know, it's basically zeros and 4 1s or minus 1s in different places. So they all work magically on this, and they all get screwed up by the fact that there's 3 non-zero terms here. Okay? So that might leave you to wonder, well, you can't use Sx, Sy, Sz. What can you use? Well, I'm gonna get a guesser. Here, Cameron. What I want you to do, basically what we've just proven, so it's not SZ, SX, or SY that will work. We need a spinor component operator. So we need the component of spin in some direction. And I just want you to think of, just can you guess a direction which is special in this story?
For angular momentum direction?
Well, no, spin is angular momentum. This is a very interesting link, but we're not going to use angular momentum direction. Rather, we will use their linear momentum direction. What I have in mind is taking the momentum of the, so there's two ways you can look at it. You can look at it as the spin along the direction of their motion. Okay? So this is saying, so this, in this case, the momentum is arbitrary. It's got px, py, pz components. And then x, y, z, their spin operators all suck, okay? It's not eigenstates. However, if I take one of my axes along the direction the particle's traveling, then maybe that story is special. Now there's two ways to do that. I could give you px, py, and pz, and then you can figure out what's the direction. It's a headache. You know, I'll give you px, py, pz, you find the angle with all respect to all this stuff, and then you set up the spin operator in that direction. Or I can just say, let's take the momentum of the particle along the z-axis. Then sz becomes this operator. Does that make sense? In this story, I'm not telling you what direction the particle's moving. And then sx, sy, and sz don't work. But if I say, okay, I'm just going to say, I'm going to pick my coordinates so that the z-axis is along the direction of motion, then the spin along the momentum is the z component of spin. To figure out what happens, we just take px and py everywhere it appears and set it equal to 0, which is clearly going to give us what we need, because this term is going to vanish. This term is going to, you see what I mean? Does everybody follow? Because I'm now going to write down what happens. Okay, so if we say this, then basically sz on psi 1 is h bar over 2, 1 minus 1, 1 minus 1, acting on a e to the I p mu x mu over h bar times e over mc squared minus pz over mc 0, 1, 0, which is equal to h bar over 2 times psi 1. Okay? Again, all I'm doing is I'm taking px and py and setting them equal to 0, and then this works. Yes?
Why do you have p mu x mu there, and in the other equation you have k mu p mu?
Why do I have p mu x mu? Oh, sorry. Sorry, I should be having p mu. Sorry, I should have p mu here. No, sorry. Oh, sorry, this should be p mu x mu. That's my bad. And I can do either one up or down. There we go. Yeah. Yeah, there we go. Sorry about that. Thanks for pointing that out. Okay, now I'm going to get into a creative description because I'm tired of writing equations on the board. First of all, it might not be obvious, but a very similar story will work out if you choose the momentum along the x direction. Okay, it's not obvious at all from this, because if I say, okay, py and pz are 0, but this leaves 3 terms, but you got to remember the operator s of x is different from this. Okay, so trust me, it works out. If you don't agree with me, then I'll give it in your homework. I'm not planning to give it in your homework right now, but I will. Anybody need it in their homework so they understand it? Anybody want to derive it in your homework? Anybody want to derive everything in the class in your homework? I'm just kidding. Okay, yeah. Okay, but just trust me, there's nothing special about the z-axis. I could put the particle in motion along the x-axis and then define or look at the spin along the x-axis, and it'll all work out, okay? What we have created in this case are what are called Helicity eigenstates, which I often refer to as eigens, okay? Now, the story of helicity is an interesting one, and this is what's going to play that key, crucial technical ingredient in the weak interactions later on. So we've got to pound on this for a bit. And it is going to get a bit confusing and sort of notation heavy, but bear with me. What is helicity? Well, let me first and foremost argue that characterizing spinors in motion by their helicity is very similar to characterizing spinors by the z component of their spin. Like you have these, plus and minus solutions, et cetera, et cetera. And in fact, what we can say is the following. If we have a particle whose component of spin along the z-axis is plus a half h bar, then what we can do, so we've got sort of, and I guess I'll draw this picture. So we've got, draw like this. So we've got a particle whose spin has a positive h bar 2 over component along the z-axis. Notice I'm not saying anything about the sy or the sx. Are those 0? Is the sy and the sx component of the spin of this 0? Well, I'm drawing that arrow, but what should I really draw? Yes, exactly. I should draw a cone, where it's obvious the z component of this is plus h bar over 2, but you never know the x and y. You can't know them because remember si, sj is not 0. So you can't measure sx, sy, and sc, any two of them together. So if you know one of them, you don't know the other two. So what this cone tells us is that the spin is pointing along the positive z direction, but I don't know if it's positive y or negative y, positive x or negative x. I don't know, can't know, okay? But at any rate, taking this, I can reverse this, not physically, but descriptively. I can keep the spinner in the same direction, but just flip my coordinates. Because I can always freely choose any coordinates that I want. So if I flip my coordinates with z now pointing down, and y pointing this way, and hold on. So yeah, and x still pointing this way. Then at any rate, I just want to maintain a right-handed coordinate system. Then my spinner still points like that. I'm not doing anything physical, I'm just changing the description. But now sz would measure minus h bar over 2. Okay, I can change the spin of something, the component of spin, not the magnitude of spin, but the component of spin just by changing my coordinates. Okay? Helicity is similar. Okay? If the spin along the direction of spatial momentum is plus h bar over 2, then what we have is that the momentum is pointing in the direction to the right, and the spin, and I'm just going to draw a little vector. I'm not going to worry about the cone anymore. It's the same story. You just never draw a vector for spin. You always draw a cone. But anyway, the spin points along the momentum. So the component of spin along the momentum direction is positive. if the eigenvalue is plus h bar over 2. Okay? Or again, I could replace this with a cone if you don't understand why. Okay? Now, you ready? In this case, I could, by changing my description, reverse the order of this, reverse the direction of the spin. Can I reverse the direction of this spin? Can I, looking at a particle moving in that direction with some velocity, can I reverse its velocity? Just by changing my description.
Only if it's massive.
Yeah, so what can I do?
Just move faster than it.
I can move faster than it. Remember, if there's an ant crawling and I'm at rest, the ant's going that way. Now if I start moving, even though the ant is crawling this way, it's now moving that way, according to me. You can always boost past something that's moving below the speed of light. Okay? So we can boost, and I should say this is rotation, we can boost to a frame, and I'll call this the frame S. We can boost to the frame S prime where the momentum is reversed, but that doesn't touch the spin direction. Okay? So having boosted, we now would measure the P component of the spin as minus h bar over 2. Okay? So once again, we have this extreme similarity between picking the spin along a coordinate axis and picking the spin along the momentum. You can reverse them. Okay? Well, you can always reverse these, but you can't always reverse these. When can't you?
When it's massless.
When it's massless. Because if something is massless, and it's moving to the right with a momentum p, there's no frame you can go to which will change the direction. Because to change the direction, you have to move faster than the particle. The particle's moving at speed c. You can't go faster than that. Let that digest for a moment. Yeah.
So could we not also reverse the spin in the direction of momentum just by rotating our coordinate system 180 degrees?
No, because this is defined in terms of the direction of the momentum. It doesn't matter what coordinate system you're using, this is going to be the momentum direction. This is a physical quantity. These are just coordinate quantities.
Gotcha.
Here we've got this physical quantity which is defining it. So we have to have this reversal of the physical quantity in order to achieve that, and we can't do it. Okay? So if a particle is massive, we can always reverse this. If it's massless, if it has this, it always has this. If it has this, it always has this. Does that make sense? Notice that's different than this story or this story for massive. In this story, you can have SZ plus or you can have SZ minus just by a change of coordinate system. If you're massive, you can have plus, or if I just change my reference frame, I can change it to minus. However, if you're massless, you can have this change, but you cannot have this change. You are always going to have plus h bar over 2 for your helicity. If you have it at any time, it's always going to be that. And it's always going to be minus if you have minus at any point. Okay?
So the
Yeah.
spin in the direction of the momentum is always the helicity?
Yeah, so the spin in the direction of the momentum is what we define as the helicity of the particle. Okay, so helicity is the spin along the direction in which the particle's moving. And that can be plus or minus. It's basically if the spin is aligned with the momentum, it's plus. If the spin is anti-aligned with the momentum, then it's minus. Okay? Now here's a very, very important observation. Because having positive helicity for a massless particle means it can never be turned into negative helicity. And conversely, if you have negative helicity as a massless particle, it can never be turned positive. You might as well think of these as two different particles. There's positive helicity, massless particles, and then there's negative helicity, massless particles. And you can't change one into the other. Okay? That's not true for massive particles or if you're doing rotations. Okay? But massless particles have this very special property. And this is that key thing which is going to play a very important role later on. Okay, that's why I'm drilling on it. Okay, well, all right, fine. So what we can do is we can think of SP equaling plus or minus h bar over 2 as states of different particles. Plus is one type particle, negative is another. Now what I want to do first is I want to go back to the counting of degrees of freedom. Okay? So you might or might not remember, but when we did the counting of degrees of freedom using this Wigner classification mechanism, what we said is we could define the allowed spin states by basically choosing the 4 momentum and then considering transformations which leave that 4 momentum unchanged. So in the massive case, we could go to the rest frame, in which case P mu is MC 0 vector, or I'll do 0, 0, 0. And then we very nicely realized that even though this is 4-dimensional physics, the transformations which will leave this momentum invariant are rotations. And so you can actually classify the spin under SO3. Okay? And so we discovered that the counting of the number of degrees of freedom in these things in this story for the massive case basically is the same as the counting of the degrees of freedom in non-relativistic quantum mechanics in 3 spatial dimensions. It's 2. Okay? However, if m is equal to 0, then this momentum is not allowed. Okay? Well, it turns out there is a preferred momentum that we can work with, and that is we might as well align the non-zero spatial momentum with one of the axes. So for example, if I choose the x-axis, then the 4 momentum turns out to take that form. Where this is just px, but it turns out it has to have the same magnitude as this, because the 4 momentum of this, if it's massless, has to be 0. And so if you take the dual of this, which puts a minus there, and then you go back to multiplying that by the original vector, you get minus e squared over c squared plus e squared over c squared, which is 0. So that's how you know that this component has the same size as that one, but that's just a detail. Okay? The important question is, what transformations can we do? It'll leave that invariant. We can do 2-dimensional rotations versus 3. Okay? Well, we're doing rotations now. So let's ask ourselves, can we change the spin by doing rotations? Remember, it's these boosts, which we can't do. So let's ask if we can just do a rotation and reverse the direction of spin. Okay? So if I'm in this case where I'm moving along the z direction, then you can imagine at the z-axis, at the x-axis, I have the y-axis, and my particle spin points like so, where I can think of this as actually a clockwise rotation in the xy plane. Okay? Now this is in 3D. in 3D, I'm allowed, and this is this story here. In 3D, I'm allowed to do a three-dimensional rotation, so I can take this and I can say, okay, fine, I'm just gonna reverse the z direction, and do so, in which case, the spin is now in the negative z direction. So for this case, I reverse the spin. That's exactly the way the story played out up there, okay? Now let's go to the massless case. In the massless case, it's 2D, it's not 3D. Okay, so in the massless case, what we have is a 2D where the spinner you should really think of as some orientation, not draw a vector in the third dimension, because that's actually not how spin is defined. We think of spin as a cross product. Don't think of cross products as vectors where it points orthogonal. That doesn't work in 4 dimensions. Just think of it as the curl, as the contour of the positive or counterclockwise or clockwise contour. But anyway, so this is the 2D story. Okay? Well, I can do this all day long. I can do rotations in the XY plane, and that's not going to change the story. Okay? So it turns out that not even by these coordinate transformations can I reverse the direction of this spin. So this is a very intrinsic property of massless particles, which you just can't shake. Now, what we want to do now is we want to go back to the Dirac equation and ask, okay, how is this reflected in the Dirac equation? Is it reflected in the Dirac equation? And it turns out it is. And this is where things are going to get really ugly, but bear with me. Okay, yeah. All right. So first of all, recall that boosts on spinners are generated by these sigma 0I matrices, which are I over 2 times sigma I 0, 0 minus sigma I, where sigma are the Pauli matrices. Again, this is a 4x4 matrix, all right? While rotations on spinners are generated by sigma ij, which is 1/2 epsilon ijk sigma k 0, 0, sigma k. Okay? Remember this labeling here, 0i, ij, this is obviously space-time indices, because boosts are transformations between the time direction and one of the spatial directions, whereas rotations are just transformations between purely spatial directions. Okay? All right. So, so if we take a 4-component spinner, psi, then by looking at these generators and their sort of block diagonal form, it kind of becomes obvious that maybe we should think of the spinner in terms of an upper component and a lower component, psi plus and psi minus. So psi plus has 2 parts and psi minus has 2 parts. Again, this is a notational nightmare, but bear with me, okay? Where psi plus minus transform oppositely under boosts, obviously because the psi plus term gets a plus sigma I and the psi minus term gets a minus sigma I, but they transform alike under rotations. Okay, because you got sigma k, all right? The two component contributions, psi plus and psi minus, are called Weyl spinors, or chiral spinors. Okay? All right. So again, the full spinor is 4 components. I can kind of take the upper 2 and the lower 2 and kind of this plays a certain role, this plays a different role. And now I'm just going to say, okay, I'm going to consider this 2-component thing and then this 2-component thing, give them different labels. And these 2-component objects are called Weyl spinors. And don't worry, why you've got 2-component objects versus 4-component objects is going to be clear in just a second, okay? So now what we can do is we can take the Dirac lagrangian, which if you might not remember is h bar c psi bar gamma mu d mu psi plus mc squared psi bar psi. And we can, instead of using the psi and the psi bar, this is just the conjugate of psi, instead we can write it in terms of psi plus and psi minus. And this is going to give us a really useful insight. So this next step is not at all obvious. That's why you're going to do it in your homework. Okay? But this is what we end up getting. Minus h bar c I psi dagger minus d mu sigma mu psi minus. Put that down there where it belongs. Plus I psi dagger plus d mu sigma bar mu psi plus, okay, where this thing is defined as I and sigma I. So this is a 4-component set. The 0th component is just the identity, and the spatial components are the 3 Pauli matrices. That's what this sigma mu is, okay? And this sigma bar mu is I and minus sigma I. Okay? I'm just going to call it sigma bar. All right? And then, of course, we get a term from the masses. So this expression right here is just coming from this kinetic term. And then we get a term from the masses, and the mass term is going to be pretty simple. Plus mc squared psi minus plus psi plus psi plus psi minus. And just in case you don't remember, psi bar is defined as I psi dagger gamma 0. So it's not just the Hermitian conjugate times I, but rather we had to throw in this gamma 0 term, okay? So, okay, that looks interesting, right? Now let me ask you a question. We've got these 4-component spinors, the solutions to the Dirac equation, which is the equation of motion from the Dirac Lagrangian. If we have 4 components, that's fine to the story. What we found, though, is that we can break it up into psi plus and psi minus, but the really interesting question is, can we only use psi plus? Or only use psi minus? Do we have to have all 4 of them in the story? I mean, these are transforming very differently. They're really disconnected. So maybe we can take just the psi plus, in which case we can describe everything that's going on with a 2-component object, or just the psi minus, in which case we can describe everything that's going on with just a 2-component object, instead of this big-ass 4-component spinor. Yes?
Sorry, what are the sigma mu and sigma mu bars again?
Sigma mu is, it's a 4-component thing, because that's it's got a time-like component and an XYZ. The time-like component is just the identity. Okay? And then the the rest of the components are the sigma I. These are 2x2 matrices. Because remember, psi minus is only a 2-component thing, so you're acting on it with a 2-component or 2x2 matrix. So this is the 2x2 identity, and these are the 2x2 Pauli matrices, which we've written down at some point. Psi bar, or sigma bar, is I and minus sigma I. Did you get that?
Yes.
Okay. So once again, like this is writing it in terms of 2-component spinors. This is in terms of 4-component spinors. What I'm asking you is, can we just go from here to just psi plus? Can we do it? Oh man, I'm gonna draw a card on this one. This is a good one. Dang. Davis.
I don't think so.
Why not?
Um,
Well, I mean, look, if I want to drop out sigma minus, then I just make this term go away, and I use this term, right?
Yeah, but then you have the MC squared on that.
Yes. This is the fuck up factor. Okay? This, if I make psi minus 0 and just keep psi plus, both of these terms are 0. All right? Well, is there any special type of particle that you think you might be able to do this for? You can do it for a massless particle. Because for a massless particle, this whole term is gone anyway. If a particle has mass, you gotta have both parts. Does that make sense? That's gonna play a very important role later on. That's why I want you to just digest this. For massless particles, we can actually describe them in terms of Weyl or chiral spinors alone. So they're 2-component objects. They satisfy the Dirac equation. They do all the stuff that the 4-component spinors do. It's just they're a way simpler story. That's only valid if they're massless. If they are massive, you must have both, in which case you have to work with the 4-component, and this is often called the Dirac spinor. It's the solution to the Dirac equation. It's the Dirac spinor. So the 4-component spinors are Dirac spinors. These 2-component things, which you can really only use separately if they're massless, are called Weyl or chiral spinors. Okay? Now, if we can do this, then it turns out that the equations of motion satisfied by these are simplified. So we get I sigma bar d mu psi plus equals 0, or I sigma, or sorry, this is sigma mu, or I sigma mu d mu psi minus equals 0. Okay? These are often called the Weyl equations instead of the Dirac equation. They're just a simpler version. Okay? Now, it turns out, rather interestingly, that for massless particles, working with this state versus this state is exactly the same as working with plus or minus chirality states. Let me show you. So first of all, let's start with psi 1, which of course is A, and I'm just going to go back to this, the full board solution, A e to the I p mu x mu over h bar e over mc squared minus pz over mc minus px over mc minus I py over mc 1, 0. All right. If I take the momentum to be along the z direction, okay, then of course this simplifies to A e to the I p mu x mu over h bar e over mc squared minus p over mc 0, 1, 0. a minute. Is this an eigenstate of SP, which is SZ in this case? Yeah, I mean, remember this is SZ, which in this case is SP. I'm just gonna get a contribution from this and this, okay? So this is an eigenstate of SP. Is it an eigenstate of pure chirality? That is this either psi plus 0 or 0 psi minus? Nope. So what I want you to notice is in the massive case, a state which is the eigenstate of this chirality in a sense is not basically a Weyl eigenstate. I've got to be careful using Weyl versus chiral, okay? But, or, I mean, actually, I shouldn't say that, I should say helicity. So here we're talking about an eigenstate of a helicity operator. Chiral is actually attached to Weyl. So chiral is more attached to the Weyl terminology, and then helicity is just basically the spin along the direction of momentum. However, in a moment, they're going to become the same. But just notice, even if we align the motion with a coordinate axis, and then we use that coordinate axis to define the spin operator, which is how we define the helicity, this is an eigenvalue of the helicity, or it's an eigenspinor of the helicity operator, but it is not in one of these chiral forms. Now, we take m to 0. If you take m to 0, first and foremost, you should remember that e squared minus p squared c squared is equal to the mass squared times c squared, but if it's 0, this is 0. Well, you can take this and determine that this term right here is exactly 0. So in the massless case, this becomes e to the I p mu x mu over h bar times 0, 0, 1, 0. Now, is this massless story still an eigenstate of the helicity operator? Heck yeah, even more so. You ain't got to worry about that term. But is it now a Weyl state? Yes, it is. Okay? So in the massless case, Weyl or chiral spinors are the same as these helicity eigenstates. That is not the story in the massive case. Are we clear on that? So what I'm trying to get you to see is that massless particles, in terms of their way their spin story plays out, massless particles very different than massive particles. Massless spinors just get simpler and simpler. You can take them from 4 to 2 components if you want. You cannot do that with massive spinors. All right? Okay. Whew. How far am I going to go? I'm going to go a long way. No, I'm not going to go that far. Okay. All right. Now, one thing I should say. Every single detail of what I've done has hung kind of critically on the form of these matrices, the form of these spinor, or these spin component matrices in the 4x4 spinor space that they act on, okay? And these are born from the gamma mu's. Remember those gamma mu's? Okay, you build these from the gamma mu's. However, I think I told you early on that there's plenty of different versions of what gamma mu's can be. Okay, it's not just the set that I wrote down of 4 gamma matrices. You can just work with a different set. There's a variety of sets of gamma matrices that you can use. And those gamma matrices take very dissimilar forms, like the gamma z, or the SZ component coming from a different choice of the gamma matrices definitely doesn't take this simple form, okay? So we have 2 ways that we can explore this. One, we can say, fine, for every different convention, And these are just conventions. They're all describing the same physics. But for every different convention, I'll play out the entire damn story and see that it works out in detail. Or maybe we can define things in abstract enough ways that what we write is true no matter what version of the gamma mu's we use. That's a more powerful way to go. Okay? So who wants to see that? Good. This is where the gamma 5 matrix comes in. Remember gamma 5 from your last homework? I just defined it for you, but now we're going to see its use. Okay? So gamma 5 plays a critical role in sort of defining all of this without the explicit use. I mean, you can get an explicit expression for it, but you don't need it because you can do a lot of this with gamma 5. So let's see what we can do with gamma 5. There it is. Okay, so first of all, remember gamma 5 is defined as minus I, gamma 0, gamma 1, gamma 2, gamma 3. Okay? And it's basically 1, 0, 0, minus 1. Okay? Now, what we can do, and remember gamma mu, gamma 5 is minus gamma 5, gamma mu. What we can do is we can take this nice operator right here and we can form a projection operator from it. Basically taking 1/2, 1 plus gamma 5. Okay? And then if we act on a 4-component spinner with this, we'll have 1/2, 2, 0, 0, 2. Oops. 0, 0, 0. Okay, hopefully it's obvious. P plus is 1/2, 1 plus this. The 1s here combined to give you 2s, divided by the 2 gives you 1, and the 1 from here and the minus 1 from there go to 0. And if this acts on a spinner where I distinguish the psi plus from the psi minus, this projects you into the psi plus state, whereas P minus on psi projects you into the psi minus state. Okay? Now here's the thing, from the definition, of gamma 5, you can show that 1/2, 1 plus gamma 5 is a projection no matter which gamma mu's you use. So you can use any representation of the gamma matrices, the Dirac matrix. Yes?
Should it be 1 plus or minus gamma 5?
Yeah. I mean, they're both projection operators, but yeah, plus or minus. Okay? Does this sound reasonable? Good, I'm glad it doesn't, because you're going to prove it in your homework. It's given. Okay? I just want to point out where things are coming from the lecture into your homework. So instead of, what we can do is instead of saying, okay, I'm going to start with this solution, this 4-component solution, and I'm going to call the top 2 components psi plus and the bottom 2 components psi minus. And this is where this becomes one of those sort of abstract steps which you won't appreciate till later. This solution, this 4-component solution, which we found we could divvy up into 2 different chirality solutions, this is all hanging on the particular gammas that we used. Okay? So what we can do if we want to say something more general is we can skip this, and instead we can define psi plus, the positive chirality solution, as P plus times any solution using any convention, because look, if you change the gamma matrices, that's gonna change the form of these solutions. Every part of the story changes. But now we can use this definition in terms of the projection operator to say, it doesn't matter what convention you're using. If I want the positive chirality piece, I just hit it with this projection operator, which is universal. And similarly, the negative chirality piece I get from the other projection operator. So it might turn out that this thing is not the upper two components. It might be the first component, the fourth component. It might be the first and the third. I don't know, it doesn't matter. This is going to be a positive chirality state. This is going to be a negative chirality state. Okay? All right. Let's see. I really want to say this just to get through it, but so let me just scribble down a few more things because I really want to get this done, and so that next time we can move into what we're planning to move into next time. So I'm just going to kind of do a cursory thing of what's on the next couple of half pages, and then we'll get out of here. First of all, actually, that one I'll skip. So there's a discussion of parity in there, but I'm going to skip that for now. I'll come back to it later. But now I just want to show you what kinds of things you can build using this technology. So first of all, remember that we have quantities like psi bar psi, which actually are what they transform how in spacetime. How does psi bar psi transform in spacetime?
Should be invariant, right?
Yeah, it's a scalar. Remember, how something transforms in space-time is indicated by the number of vector or dual vector indices. Okay, so psi bar psi is a scalar. What about psi bar gamma mu psi? What is that? How does that transform?
Vector.
That's a vector. Yeah, good. Okay. Oh shit! No, I gotta talk about parity for a minute. Do you guys mind staying 5 minutes late so I can just get through this? If you gotta go, go. Don't worry. You can watch this in the end of lecture. But I just want to bust through this so I can start with the new stuff next time. Okay, so let me just very quickly define parity for you. So parity is a transformation which takes the zero component of anything to the zero component. It doesn't do anything with the time-like direction, but it takes all of the spatial directions and reverses them. Okay? So parity is that transformation which early on when we were talking about SO3, you know, you talk about rotations, and I said if you flip all of the axes, if you flip them all, then that's a transformation which you can't get from rotation. That's a parity transformation. It's basically flipping all three of these. You can also define it by flipping only one of them, but it's more democratic to do all three. You can't do it with two, because if you invert two axes, that's equivalent to a rotation, remember? I went through that before. But anyway, so we're going to define parity as a reflection in all three spatial axes. And this is not a part of SO1, 3. Okay, this is not part of that. All right. So what's important is that it leaves the signs of rotations invariant, but reverses the signs of boosts. So BTX, BTY, and BTZ. Now, if we look back at how we define psi plus and minus in this story, remember psi plus and minus transform with sigma k for rotations, but plus or minus sigma I for boosts. Okay? Yeah, that's up here. All right? So we can immediately infer that if enact the parity transformation on psi plus minus, then what that's gonna do, are you ready? It interchanges them. Okay? So the action of parity on a Weyl spinor is to convert it into the alternate form. So if it's a psi plus, it turns it into a psi minus. Now notice, parity transformations, these are not elements of SO1, 3. You can't do this by rotating the coordinate system or by boosting. You can't do that, period. This is a different kind of transformation. Okay? Whether or not this is a symmetry of nature is an interesting question, and one we'll talk about in due time. Okay? But at any rate, for the massless case, this is what we expect for helicity states. Because after all, if I have spinor, momentum, so that's a positive helicity state, SP plus h bar over 2. This is the psi plus state. Then a parity transformation is going to reverse the momentum. It's going to keep the spin in the same direction. That's going to turn it into psi minus, which is the helicity eigenvector associated with the eigenvalue minus h bar over 2. Okay? So this is all that the parity transformation is doing. It's reversing these things for us. Okay? Now, coming back to this story, I can ask, all right, psi bar psi is a scalar under what set of transformations? Any takers?
This, SU?
Well, I mean, yes, but rooting it back in the space-time transformations.
SO13?
Yeah, everything is based on this. So it's a scalar under SO13. This is a vector under SO13. But now we can ask, how does this transform under a parity transformation? Okay? Well, it turns out that one way of giving the spinorial definition of a parity transformation is we say P is I gamma 0. Okay? I've already set it up here. No, that's not my parity. This is my parity. Okay? So it turns out that this does this for me because gamma 0, this just becomes 0, 1, 1, 0. Okay? So the parity transformation is going to act like that. And so if we take the scalars, we can say, okay, fine. Under parity, this is going to go to psi bar minus I gamma 0 dagger, I gamma 0 psi. What is this? And this is equal to psi bar I gamma 0, I gamma 0 psi, which is just psi bar psi. Okay? If you just multiply these matrices out, you'll find. So if I do gamma 0 dagger, that's just going to bring out overall minus sign, which cancels that, leaves me with I gamma 0, and then I gamma 0 times I gamma 0 is 1. Okay? So this is basically a scalar under parity as well. All right? So then, obviously, the vectors transform as psi bar gamma mu, and the details are written up, but I'm going to skip them for now. This goes to psi bar gamma 0 psi minus psi bar gamma I psi. That is, the time-like part of the vector remains the same, but the spatial-like part of the vector changes sign. Gets a minus sign. Does that make sense? That that's what happened under parity? Yes. Parity is not doing anything to the time-like piece, and it's reversing the order, it's reversing the sign of all of the spatial pieces. So that's basically going to take the spatial part of this vector and reverse it, leaving the time-like piece alone. So this is a vector. Okay? So then we can look at two alternatives. First of all, I can look at psi bar gamma 5 psi. How does this transform under SO1, 3?
pseudoscalar? I'm trying to, so under parity transformations, it requires to make it.
As said, SO1, comma 3, Ross. Under SO1, comma 3, it is a,
Pseudoscalar.
it is a
Oh, scalar.
scalar, thank you. This is a scalar under SO1, comma 3. This is why I never let you answer questions. You go way too far. Under SO1, comma 3, this is a scalar. Then we have to ask, what about a parity transformation? And under a parity transformation, this actually transforms with a negative sign. So that's different than psi bar psi. So we call this a pseudo-scalar. Thank you. And then, I know, if we take a vector and we transform it, then it's going to transform into, under parity obviously, minus psi bar gamma 5 gamma 0 psi, and then plus psi bar gamma 5 gamma 0 psi. So this is going to transform as a pseudo vector. Okay?
Both of them? Are those added?
Oh, sorry, this is me, or this is I. Sorry, this is I. So again, the time-like and the spatial-like pieces are doing different things. Okay? Okay, so we've been able to build scalars and vectors, but with this gamma 5 and this whole notion of parity transformations, we're also able to build pseudo-scalars and pseudo-vectors. Now, how many of you have ever worked with a pseudo-vector? You've all worked with a pseudo-vector. The cross product between two vectors is at best defined as a pseudo-vector. Right? If I'm taking V1 cross V2 and I reverse both of them, I get the same result for the cross product. The cross product does not reverse. Because the two vectors are crossing reverse direction, but their cross product is still the same because the minus is canceled. At any rate, go home and look it up. All right, I'm done for today. In the end of the notes, and sorry, oh my God, I kept you 10 minutes late. I'm sorry. And is there a crowd waiting out there? You guys keep looking out the door like there's somebody out there. At any rate, remember at the end of today's notes, I've got a solution to the Dirac equation in terms of the four component spinors. I just don't want to go through that in detail in class. You can look at it if you want. Thank you. Sorry for being late, but fortunately next time we'll get to start out clean with a good story.